Good afternoon. Today we're going to talk about Big O, induction proofs with inequalities, and we're also going to give a couple of hints on homework 6 because I've seen several people make the same mistakes, so let me reiterate a couple of points for you. So let's start with that. One of your homework problems says that you need to prove that 1 plus 1 factorial times 1 times 1 factorial plus 2 times 2 factorial plus ... plus n times n factorial is equal to the quantity n plus 1 factorial minus 1. And it says to prove this by induction. So in your basis, what do you need to write? Basis, n equals 1. So what is the left-hand side?
1.
1 times 1 factorial.
1 times 1 factorial, which is equal to 1. The right-hand side is what?
2 factorial minus 1.
1 plus 1 quantity factorial minus 1, which is 2 factorial minus 1, which is equal to 2 minus 1, which is equal to 1. Okay, nobody's really having a problem with that yet, except they may have forgotten to do the basis, which is very important, right? Because if you don't do the basis, you might not as well do the proof. Now, this is what I saw in some papers, and I would like for everybody to try to help me find what the problem with it is.
What is that on the left hand? What's that in the middle there? A dot of the left hand side of the fact? You got
Those are times.
Multiplication.
Times.
Oh,
Those are dots. Yes, they're times.
The left-hand side is supposed to be a sum.
The left-hand side is a sum. It has more than one term. In this assumed statement, I have only one term. So at a minimum, you should make sure at least that the thing you write down has the right number of terms. So this doesn't have the right number of terms. If I wrote 1 times 1 factorial plus 2 times 2 factorial plus ... plus n times n factorial equals this, that would be fine. Or I can write it in summation notation, which always helps because then you make sure that you have the right thing, right? So how do I write this as a summation?
K equals 1 to the n.
It has n terms, so it's good if I go k equals 1 up to n. And then what goes on the inside?
K times K factorial.
K times k factorial. That's excellent because if I had written n times n factorial, then every single term would be the same, and it would be n times n factorial, right? So I have to have k changing because the number changes each time. The first term has 1 times 1 factorial. The second one has 2 times 2 factorial. The third one has 3 times 3 factorial, and so on. So all of that is equal to n plus 1 factorial minus 1. So now writing my proof step is a lot easier if I write my assumed step correctly. Right? So if I write that correctly, I know now on the left-hand side all I have to do is change the summation, the top of it. So prove summation k equals 1 up to n plus 1 of k times k factorial is equal to n plus 1 factorial minus 1. That right-hand side is equal to n plus 2 factorial minus 1. So what's the first step of this proof? Write down the left-hand side of my proof statement, right?
Yeah.
So if I write down the left-hand side of my proof statement, I write summation k equals 1 to n plus 1 of k times k factorial. Then I write it in terms of my assumed statement, right? But I have to fix this, right? So it's plus something.
N.
n plus 1 times n plus 1
That
factorial.
term is the last term of the summation, which would be n plus 1 times n plus 1 factorial, right? What's the next step in this proof? Substitution, right? So I substitute in here. So when I substitute that in from the assumed statement, I get n plus 1 factorial minus 1, and then this comes down. Okay, my final step just needs to make sure that I get that that's equal to n plus 2 factorial minus 1. So the minus 1's already in there. You just have to get that this other stuff is equal to n plus 2 factorial. I'm going to leave that to you. It's worth 2 points. Okay. But be very careful with these. If there's a sum, make sure that you put a sum. Make sure that you put a summation or write out all the terms. I don't care which one you do. It's good to practice getting summations, though, making summations. Are there questions about this one? My advice on this one is when you look at this summation, if you look at the right-hand side here, you see n plus 1 factorial in both of those. If you factor it out, what do you get? This is just a 1 in the first term, right?
Mm-hmm. Yeah.
Sorry. And the next term is n plus 1. So I'm going to get n plus 1 factorial times the quantity 1 plus n plus 1, which is n plus 2. Right? And then n plus 2 times the quantity n plus 1 factorial is the same as n plus 2 factorial. And if you don't believe me, you need to verify it. Okay, and I'm saying that because this is your homework and I don't need to do it on the board for you. Okay, so even if I've already worked a problem for you, you can copy it out of your notes anytime you like to, but I would like for you to work it again. Because if you can work it again by yourself, you'll be able to do what? Take the test. There you go. Okay, so the very same thing needs to be done on the other summation in part 1 of your homework. And in part B, problem B in part 1 of your homework, we have that n factorial is less than n to the n. First of all, how can you verify to yourself that that's true? What?
Make a table.
I could make a table, so that's one thing. That's good. And then that tells you where you can start your basis, right? I can't start my basis at n equals 1 because it's not true, right? If I'd use a less than, it's not true. If I use less than or equal to, it would be true, right? Because then I'd have 1 factorial is less than 1 to the 1. Less than or equal to 1 to the 1, then it would be fine. So I have to start with n equals 2. The other way I could do is examine the terms on both sides. So both of these are products, right? On the right-hand side, there's n terms, and all of them are the same. On the left-hand side, there's n terms, and they're not all the same, but all of them are less than or equal to n, right? So it would make sense that n factorial is less than n to the n because most of the terms in the product are smaller and there's the same number of them. So you can verify to yourself that that makes sense. So that now anytime you see n factorial and n to the n, you know which one is bigger. And if you forget, you can just say, okay, how many terms are in each, and then which one has smaller terms. So then if you want to do this proof, you have to do the same way. You have to prove a basis. You have to write assume, and write down the whole thing. And then write prove what?
N plus 1 factorial is less than n plus 1 to the n plus 1.
So that's n plus 1 to the n plus 1. It's in your proof statement. And then you start with the left-hand side of your proof. This is exactly the method that we've done before. We start with n plus 1 factorial. We write it in terms of the left-hand side of what we know. N plus 1 factorial is equal to n factorial times what? Times n plus 1. Just keep practicing with it and you'll get used to it. Because a lot of the problems that you might have with this class are just notation problems because you're not used to using factorials or logs or whatever function we happen to be dealing with, summations. So now, I know something about n factorial, right? I know that it's smaller than n to the n. So if I were to take this and replace the n factorial with n to the n and just leave the n plus 1 there, then what operator goes right here? A less than goes there because I replaced exactly one term with something that's larger and left the rest of it the same. So if you look at it this way also, this is equivalent to taking the assume statement and multiplying both sides by n plus 1. So that's how you can double check that it's the right answer also. So now this looks a little bit closer to n plus 1 to the n plus 1, right? Because I don't have any more factorials in there. That was good. Now this is what I usually do in my less than or equal to proofs, and we're going to talk about this some more. I want that n to the n times n plus 1 is less than what? What would be really cool?
Is less than n to the n plus n.
It would be good if it was less than the right-hand side of what I was trying to prove, right? Because then I would be done, because I would have that n plus 1 quantity factorial is less than that, which would be less than what I wanted to prove. So sort of like hypothetical syllogism, I would know that n plus 1 factorial would be less than n plus 1 to the n plus 1. So if I knew that, I would be golden, right? I'd be able to use these two statements together to get what I wanted to prove. So now this is sort of a new little proof that I'm going to do. Remember how in our proof that square root of 3 was irrational, we wanted that if 3 was a factor of p squared, that it was also a factor of p? When we went and did a side proof, that's what we're going to do here, the same kind of thing. So here, I want that this is true. If I can find that that's true, I'll be done. So I could divide both sides by n plus 1. Right? And then I'll get that n to the n is less than n plus 1 quantity. How many are left? N of them. You can look at that and tell that's true, right? Because the terms on the left, there's n of them. Terms on the right, there's n of them. And all the terms on the left are smaller than all the terms on the right. So this is true, so therefore this is true. Right? So therefore, n plus 1 factorial is less than n plus 1 to the n plus 1. I'll put little parentheses around there. So it's still the same procedure as an equals, but instead of, in our substitution part, instead of using equals, we use whatever the sign was in the assume.
What would the basis be for that?
That's what you have to figure out. You have to plug in some value for n and verify that it's true, right? Okay, so when we're talking about big O, we're going to do lots of inequality proofs. So I started last time with a definition of big O, which is kind of intimidating, but it really means something fundamental. It really means something that you can understand and get a hold of. Okay, so I'm going to make a picture, and then I want us to organize the picture. I'm going to put a bunch of functions in there, and we're going to compare them by sizes. All right? So here's a big picture. I'm making a big set. Okay, now, if I didn't care about constants at all, which one of these is the smallest function? If I just ignore constants.
N.
5,000.
5,000 is the smallest because I'm ignoring a constant. So that's 5,000 times n to the 0, right? Or just 1. So if I ignore a constant, that's like 1, right? If I ignore a constant, that's like n, right? So the rest of them, I don't have constants to ignore. Those two have numbers that I should ignore with them. Okay, so now let's organize these by the smallest to the largest. Out of those, 1 we said was the smallest. What's the next smallest?
15n.
15n. Anybody vote for anything else?
Log n?
Log n. I'm going to vote for log n because n is bigger than log n. And then I'm going to say n cubed is the next biggest, and then 2 to the n, and then n factorial. We just proved by induction that n to the n is bigger. So I can go ahead and stick that in my picture too.
Where does the 1 come from?
The 1 comes from the 5,000. So 5,000 and 1 are sort of in the same category. And 15n is in the same category as n. If we're ignoring constants, doesn't matter what the number that we multiply by is. So let's draw another picture. And this is going to be a picture of what big O is like. So this is my order of functions. So like if I say an algorithm has an order of 1, it takes about 1 operation or some constant number of operations, it's going to be a lot shorter than some n cubed algorithm, right? Because n cubed takes, no matter how many, like if I have 1,000,000 inputs, take 1,000,000 and cube it, and that's how long that program's going to take. Okay, so even if I have 5,000 down here, that's better than 1,000,000 cubed. Right? Good. So now I'm going to make these functions like this. It's going to be 1. It's going to be log of n. Now, in each of these circles, I'm going to put stuff that's smaller than it. Smaller than a constant times the main function. So the main function I've written at the top. Okay, so in this first box, I can put 5,000. I can put 5,000,000. I can put any number I want to. Pi, whatever. Any number can go in there. Now in log n, all constants are smaller than a constant times log n, right? So I can put 5,000 in here. So actually I can put all of this stuff in here. Right? If all of those things are smaller than or equal to a constant times 1, and 1 is smaller than a constant times log n, then all of the stuff in here should be in there. So what else goes in log n besides the things that are in the 1 box? 2 log n, 1,000,000 log n, right? Anything like that. Any constant times that. Or even log n plus 2, right? Because that would be less than 2 log of n, right? So how about in the n squared circle? What kind of stuff can go in there? So everything that goes in this can also go in here. Any constant times n squared can go in here. Any sum of any n squared terms plus any of the lower ones is going to go in here. So n squared plus 5 log n plus 2 goes in here also. So in a similar vein, we can actually do this for all of them. Right? So all of these are actually subsets of the next one. This set I'm going to call big O of 1. This is big O of log n. This is big O of n squared. This is big O of 2 to the n. This is big O of n factorial. And this big O of n to the n. So I'm categorizing functions according to how large they are, how fast they grow. If you grow order of 1, you're in this set. If you grow order of log n, you're in this set. Or slower. You're in this set if you're that speed or slower or constant times that speed. So all the things in n squared have to be a constant times n squared or else stuff that's lower. What about n cubed? Where would I put n cubed?
Between 2 to the n and n squared.
It would go between these two because it can't go in n squared. It can go in 2 to the n because it's smaller than 2 to the n. If I make n large enough, 2 to the n will definitely get bigger than n cubed. Right? Because exponentials are bigger than polynomials. Okay, so I can get a big enough n so that 2 to the n is bigger than n cubed. Any n to the k is going to be smaller than 2 to the n. Okay, so 5 times 2 to the n is also in here. N to the k plus 3 times 2 to the n is also in here. Right, so sums, anything that's in the set, if you add those two together, it's still in the set. So these are sort of closed under addition, just like the integers. Okay, so if I'm in this set and I add two things in the set, then I'm still in the set. Now, n factorial takes all of those things. So 5 times n factorial is still in here. And any sum of any constant times factorials plus any of those smaller things is still in here. For the last one, any constant times n to the n plus any sum stay in there. So when I ask you what the big O of a function is, you ignore the constant and you figure out which one of these circles it goes in. Or if it's like n to the k, you can actually say it's just big O. Like if it's n to the fourth, 15n to the fourth, you can say it's big O n to the fourth. These aren't all the possible sets. These are just some of them, right? I could take any set and make the big O, right? Because it would just be constant times that plus anything smaller. So sometimes you might have to prove that one of these functions is in one of these circles, in one of these sets. And that's what we're going to be doing. You could alternatively also define sets like this where we have, instead of stuff, a function and everything smaller than, I could also say that function and anything bigger than that, right? So these are big O's. If I do it the other way, it's called big omega. So let's do a little picture for that. Now, I don't normally teach this, but I'm going to go ahead and do it because you have to do it next semester anyway. So in your data structures class, which is the next thing you should take after this, you will be doing a lot of comparison of functions. So you're going to be comparing, you're going to do big O and you're going to do big theta, so you should understand both of them. Okay, so big omega of 1 would actually be 1 n squared log n. Everything that's bigger than 1 would be in big omega of 1. Big omega of n squared wouldn't have any 1's in it, right? It would just have n squared plus anything else, right? Log n squared plus 1 is in there, but also n cubed is in here. Anything bigger than it goes in that set. So n factorial is also in here, right? So the only thing that's not in here is stuff that's just order 1. So big omega of 2 to the n is stuff that's size 2 to the n or bigger. So I wouldn't have any squares in there. I wouldn't have any polynomials in there unless they were added to something that was big enough. Yes?
I have a question. Like when you're doing exponentials, do you need to have different big omega sets for, like, say 2 to the n and 5 to the n?
That's a good question. I would make a different set for 2 to the n and 5 to the n. Although if I were comparing functions, I might not care too much whether it was 2 or 5.
Okay.
But I would make separate sets. Like if someone asked me what was the big O of 1500 times 2 to the n, I would say 2 to the n. I wouldn't just say a to the n and have all of the exponents in the same set.
Okay.
You can break down the functions any way you like, but 2 to the n and 3 to the n are a lot. 3 to the n can be a lot bigger than 2 to the n, so you might want to actually know that difference. So, but I don't care about a plus 1 or a plus n squared or something like that. So things in here will be 2 to the n, constant times 2 to the n, so like 1 million times 2 to the n, or even 1/2 times 2 to the n. Right, because it's a constant times 2 to the n.
Would n factorial also be there?
N factorial is also in here.
N to the n.
So this one is a subset of this, right? So it actually goes this way. Subset. This is a subset of this. So big omega of 1 takes all of the functions. Right? So the biggest one I'd probably do is n to the n, right? And this would be n to the n, constant times n to the n, and sums of anything n to the n plus anything larger or anything smaller. It doesn't matter because that's bigger still. So this is a subset of that too.
Do you combine these to get a range, or because I can understand like big O, you want to get the smallest possible runtime for your algorithm, but would you use big omega to narrow it down with big O, or what?
We actually use big O and big omega together to find functions that are the same order. So order is sort of like order of magnitude about how long it's going to take. So when functions are the same big O and big omega, then you know they're called the same big theta. So that's another diagram. So these are sort of, let me make another picture of this. So here's all of my functions. And let me make sort of rings. Let's put another big one. N to the n, n factorial. Let's say 2 to the n. N to the 10, or whatever power you like there. Log of n, and 1. So in big O, these are subsets, right? So if this was big O, then all of these are subsets. So this is big O, n to the n, which is actually the same thing as big omega of 1, except, yeah, it's actually the same thing. So they sort of go in reverse order. This is big O of 1, big O of log n, big O of n to the 10, big O of 2 to the n, big O of n factorial. These are subsets. So when I do big omegas, I'm excluding things. When I grow in big O's, I'm including more stuff. So things inside big O of 1 are smaller than or equal to that. And that's the important part. So let's not think of big O omega in this picture. This is a big O picture. So in the big omega picture, the largest set would be big omega of 1, and then big omega of log n, or something like that. But doesn't correspond exactly to this, which is why I don't want to put the two pictures together. So the complement of one is not the other one, but they're very similar. All right, so let's talk about big theta also. So we have big O. So if I have big O of f, this is f and everything smaller. Big omega of f is f and everything bigger. So big theta of f is going to be f and everything within a constant. So big theta is actually big O of f intersected with big theta of f. So everything that's in both of those is actually in the big theta. You can think of big O of f, so if g is in big O of f, then g is less than or equal to some constant times f, right? If g is in this, then g is greater than or equal to some other constant, let's say c2 times f. If I have g is in big theta of f, then that means that g is less than a constant times f and it's greater than a constant times f. They can be two different constants, but I can write both of those equations and they'll both be true. So g is less than or equal to c1f and g is greater than or equal to c2f are both true at the same time, as long as we start at some appropriate starting value. So we're talking about limits in this big O and big omega and big theta. So we're talking about when our values get larger or past some starting point. So I'm going to give you a function, and I want you to give me some things that have the same big theta as that. So 13x squared. Give me some things that grow at the same rate.
X squared.
X squared. What else?
X squared plus 1.
X squared plus 1.
2x squared.
2x squared. 1/2 x squared.
What about in log x squared? Would that be the same?
X squared plus log x would be same big theta, but
Okay.
x squared log x is not.
Okay.
Right? This is significantly bigger.
Yeah, because it's multiplication.
So this is no, because that's multiplication. If I add is okay. But x squared log x is not a constant times bigger, because I couldn't find a constant that would always be bigger than log x. So these all have the same big theta. So whenever I talk about these, I usually use x squared to denote them, so I don't confuse anybody. So I'm going to give you some functions, and we're going to figure out what their big O is. So what's the smallest big O that this could be in? X squared. Because each of these functions is smaller than or equal to a constant times x squared. Now if you want to do this in a nice, like, persistent manner that you can actually prove that this is less than some constant times x squared, then what you could do is for every term replace it by, say this would be 10x squared. I replace this log x, I'll replace with x squared, because I know x squared is bigger than log x, and 1 I'll replace with x squared, because I know x squared is larger. So that sum is less than or equal to this one, right? Because each of these is either less than or equal to. So that's equal to, this sum is equal to 45x squared, right? So for x greater or equal to 1, 10x squared plus 15 log x plus 20 is less than or equal to 45x squared. So therefore, let's say this is f of x. F of x is in big O of x squared. That's a proof. That's how you do a proof. So we're going to do some more of those. When you want to prove what the big O of a function is, we'll do that. We can do big omega the same way, and we could do big theta the same way. Except big theta, we'd have to do two proofs, right? We have to do a less than or equal to and then a greater than or equal to. We have to find constants for both of them, and we also have to have this. So we have to have these two numbers if we want a real proof. I could just look at this and say that's x squared. If I want to prove it, I need to have a number, a constant times x squared, and I need to have a starting value where it's true. Sort of like a basis and tell me the constant. Questions about this one? So this step right here is what I want you to get used to doing. Because then you'll always know the constant. So if someone made you prove it, you go, oh, this constant is 45. It doesn't matter. You don't actually have to leave the 15s and 20 out there, but you can use x greater or equal to 1 in that case. And I'd much rather use x greater or equal to 1 than having to start x large enough to make x squared bigger than 15 log x. So if I could just replace that with x squared if I made x start big enough. Right? I don't have to replace it with 15x squared. I could just replace it with x squared, but I'd have to start x bigger, right? Because x squared is 1, and that's not, well, it is. If I start x at 2, say, then x squared would be 4, and then 15 log of 2 would just be 15. So that one's actually bigger. If I want to replace it with something bigger, what I normally do is set x equal to 1 and then figure out what
does
what
that
function.
45 tell you?
It tells me that this function f is going to be less than 45x squared as long as x is bigger than 1. It tells me the constant that, I put these things in the same set, right? Same growth set. So I'm saying that f of x is in this x squared set. If you want to prove it to me, you have to tell me the constant and the starting value. So the starting value is 1, the constant is 45. Because that's the definition of the set. The definition of this big O of x squared set is that f of x is within a constant of x squared, less than or equal to a constant times x squared, as long as x is bigger than some starting value. So I have to give the start, and I have to give the constant if I want to prove it. You get to pick the start and the constant. You just pick any one that you want that works. So if you can do a proof that f is less than or equal to g of x, and you start x at some value, and you give a constant value, then you're fine. Okay, let's do some more. In this case, this method that I've shown you actually, let me just mention before we go on, that this is actually in big theta of x squared. And that's really, really easy to prove because all I need to prove is that f of x is less than or equal to the constant times x squared, but one of the terms is an x squared, right? So this sum is less than or equal to 10x squared. Sorry, 10x squared, right? Because that's just one of the terms of the sum. So the sum is certainly bigger than that.
So is that reversed? It should be greater than.
Sorry, greater than or equal to. That's why y'all were making faces at me. I was looking at you and you were like, what? Okay, so again, we had f of x is 10x squared plus 15 log x plus 20. Okay, so we already proved that it's greater than or equal to 45x squared when x is greater than or equal to 1, right? It's easy to prove that f of x is less than or equal to 10x squared for x greater than or equal to 1.
I thought it was less than or equal to 45.
I think you guys got too mixed up again.
Did I mix them up?
Yeah.
I meant less than or equal to here,
Yeah.
greater than or equal to there. Okay, so this is big O, right? So we proved that f is big O x squared. X squared goes in the parentheses. This is big omega. So f is in big omega of x squared. If it's in both, therefore f is in big theta of x squared. Okay, we're going to primarily use big O in this class. And when we find big O, I really usually want you to find big theta. But this method I just used with replacing each term in the sum with the largest term, that's going to usually give you the big theta.
If anyone has any problems with taking a picture, just raise your hand and I won't get you. If not, one or two.
You shouldn't need this back already. So if I need to prove that two things have the same growth rate, I prove that f is in big O of g and it's in big omega of g, and then I've proved that they have the same growth rate.
That's for the post office, isn't it, that picture? Did you get that? Find out what next
Just
week.
your
won't we?
pictures for the post office. Okay, so let's do some more examples. So let's say that f of x is equal to 10n, x plus x log x. So here's a question. Is f of x in big O of x squared?
Yeah.
Yes. Why is that?
Smaller
Because
than-
it's x versus x squared. X to
So
the first
x squared
power
is
versus-
bigger than x, and it's also bigger than x log x. And this is just a sum, and both of them are less than x squared, so the sum is going to be less than a constant times x squared. So I could prove it by saying that 10x plus x log x is less than or equal to 10x squared plus, I don't need a 10, just an x squared there. As long as x is what? X is greater or equal to 1. Because x log x, when I replace it with x squared, should be bigger. Because log of 1 is 0, so that's okay. So now I have that that's less than or equal to 11x squared. So I have a constant, I have a start value, so therefore f of x is in big O of x squared. If I wanted to find the smallest possible big O, then I would say that f of x is in what?
X log x.
It would be in x log x because that's the smaller of the two functions that I'm adding together. So f of x is also in big O of x log x. And I could prove that the same way I just proved this one. So 10x plus x log x is less than or equal to 10x log x plus x log x. But what do I have to be careful about here? I can't start x equals 1 because if I replace x with x log x, then when x equals 1, x log x is equal to 0, right? Which is not bigger than 1. So actually x needs to be at least 2. So if I use a big O that has log x's in it, usually start at 2. Just to be safe, because log of 1 is going to be 0. So I can double check that. When x equals 2, that'll be 2. X equals 2, that'll be 2, and that'll be 1, and that'll be fine. When I write log in this class, I mean log base 2. Because we're using binary numbers all the time. So. Okay, so now our constant would have been 11 again, right? Because this side's equal to 11 x log x. So therefore, f of x is in big O of x log x. So let's do a trickier problem with, say, a summation after you're done writing this one. Is everyone done with this?
No.
But a lot of you should have an intuitive feel of which things are bigger. It's just when you have a log or a factorial that you might need to double check some values. You can always make a table.
What was the point of doing the second one?
The second one?
Yeah.
Well, we figured that it was in big O x squared. That's just, if someone asks you that question, which one's bigger, f of x or x squared? You need to be able to tell.
And that's what we did in the first one?
That's what we did just now. Just here,
Well,
we figured out.
You have like 2 proofs almost.
I do have 2 proofs. How's that
What's
make you
the
feel?
first one for?
What was the first one for? So if someone asks you, is f of x in big O of x squared? You have some homeworks like that.
Okay, f of x.
And also, if I give you 2 algorithms and I tell you that the runtime of one is f of x and I have the other one as x squared, I need you to tell me which one's going to run faster.
Okay.
If I have lots of inputs.
And
So if I have lots of inputs, which one's going to be faster? F of x. Because f of x is in big O x squared, but x squared is not in big O of f, right? Because x squared is not smaller than x plus log x log x. You have to work on it at home if you don't get it right now. So
It's all coming from.
I'm giving you the definitions and I've given you some pictures and you need to go back and look at them. I mean, everyone knows by this point that you don't learn in this class by watching me, right? That's not the idea. You're going to learn it by doing it yourself. But I'm going to give you the definitions and the tools to do it yourself. So when you finally get it, you're going to go, oh, that's what she was doing. Okay? So the next thing that we'll do is try a function like let's figure out the big O of this sum. So big O is an upper bound. Right? So this needs to be in the... So I have a question. How many people think this is in big O of n? Okay, let's figure it out. So each one of these terms is less than n, right? So I could say that's less than n plus dot 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 plus n, right? And those would be n terms because this is n terms. As long as I have n of them. So what's on the right-hand side? That's equal to n times n, right? Which is n squared. So the big O of this is not n, it's n squared. That's why it's important to take every single term, replace it with the largest term, and then count them up.
So when you're using sums, can you use the formulas we derived before?
Yes, you could use the formulas. So I actually could have said this is a summation k equals 1 up to n of n times n plus 1 over, of k, that's equal to n times n plus 1 over 2. Big O of this is what? N squared. So yes, you can use your formulas if you have a formula for it. This is n big O of n squared. This is true when my starting value is n greater than or equal to 1. So my constant is equal to 1, my start value is equal to 1. So this is a proof that this is in f of x, f of n is in big O of n squared. And you actually can see here, this is going to be actually, that's equal to n squared plus n over 2. So that really is in big O of n squared. It's not a lot smaller than n squared. Okay, let's do another one. So here's another hard one. We have 1 factorial plus 2 factorial plus 3 factorial plus dot 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 plus n factorial. So that has n terms, and the largest one is n factorial. So this is less than or equal to n times n factorial, which is the same as replacing each term with n factorial. So I could say that this function, let's say that's f of n. I can say that f of n is in big O of n times n factorial. This is something a little bit funny with big O. N times n factorial is less than or equal to n plus 1 times n factorial, right? That's a pretty obvious step. Replacing n with n plus 1 makes it larger. That's equal to n plus 1 factorial, right? So n plus 1 times n factorial equals n plus 1 factorial. So this is also in the big O of n plus 1 factorial. And most of the time in big O's, I take out sums. So you might have someone say that this is big O n factorial, but it's really significantly bigger because I'm multiplying by another n plus 1. So I would either leave it as this or this. But you see what I mean about the plus, right? We're normally taking out pluses, but don't do it if it's inside a factorial or a power. So if you have a factorial, just leave the plus 1 in there if you happen to have a plus 1. Or you can just leave it as n times n factorial.
If you go back to the top of the screen where you have the function is less than n times n factorial, could you use something else larger than just n? Or you just wanted to...
I could have used something larger than n, but I was saying for each term, I'm going to replace each of the terms with the largest. And then that will make a bigger sum. And there were n of them, so that would be less than or equal to n times n factorial, because I added n factorial to itself n times. So I'm using the same procedure. Every time I find a big O, I have a procedure I'm just about to write down for you. So if I want to find, actually this is usually going to find you the big theta, but also finds a big O. So this is a method for finding big O. So your goal is to remove sums and constants. Because that's what makes it easier for us to understand how big a function is if we get rid of all the sums and we get rid of all the constants, we can understand the growth rate better. And that's the whole goal of this process that we're doing. So the first step is for any sum that you have, replace all terms with the largest. And this will give you your starting value For example, if I want to replace log x is less than x, is less than x, then x greater than or equal to 1 works. That tells me a starting value where that's true. So if I want to replace all the log x's with x's, starting value of x equals 1 works. X equals 0 doesn't work because log of 0 is not defined. So it tells me a starting value. Whenever I do that replacement, it tells me my start value for my inequality. So then I collect all the terms together. So like I had before, 10x plus log x, I would write that as 10x plus 10 log x, just plus x, and get x greater than or equal to 1. Works for that. Collect them up, that's less than 11x. So this gives me my constant and my start value. So I get my start value here, and this gives me my constant. The very last step,
How do you get x is greater than or equal to 1? You just know that because it's a log.
if I'm going to replace x, log x with x, then I want x to be at least 1. I don't want it to be 0.
Right.
If I was going to replace x with x log x, then I would want x to be at least 2. Right? So if I had x is less than x log x, that doesn't work until x is at least 2. Because when x equals 1, that inequality is not true. I think I just unfocused. How's that? Okay, so this tells me my start value. When I do that replacement, this replacement, I actually have to know where my start value is for that inequality, for something to be larger. Then here I get my constant after I collect them up. If there's n of them, that's not a constant. I have to leave that n on there, or x, or whatever that is. My last thing is to drop constants. So you drop them just for figuring out what the big O is. For the proof, you actually have to have the constant and the start value. So you use these two in the proof. But this is going to give you the final big O. So if I start with f of x, I'm going to get g of x here after I drop the constants.
In the second step, you said you are replacing all the terms with the largest.
That's the first step.
Oh, that's the first. For instance, it says, yeah. So number 2, you have 10x log x plus log x is less than 10x, and you
Plus
put
x.
plus x. Why did you put plus 10x? I thought the largest was 10x.
The largest term is x. So I'm thinking about big O's without constants.
Oh, you dropped the constant. Got
I
you.
dropped the constant
Got you.
for the largest term. I could have replaced it with 10x. That would be fine too. That would still work. Doesn't matter if you multiply them by bigger numbers.
So you're just looking at 10x and log x and saying which is bigger, and then you're using that as the second part to the equation
Yes, sir.
of 10x plus whatever the
Right.
largest
I
was.
compare x and log x. I decide which one's bigger. Then I actually leave all my constants. So there was a 10 there and a 1 there. I leave those. When I'm figuring out this constant right here, I leave those. And I usually like to start with x greater than or equal to 1. If I have logs, I start with 2. That's how I usually do it. You can do it any way you like. You can start x equals 100.
So for instance, if log x was bigger, would that be log x plus log x, right? Or
It would be 10 log x plus log
Okay.
x if log x were bigger, but it's not.
Okay, right. Okay.
So be careful about logs. Remember how we make logs. A log is the number that I have to raise to a power to get x. So log of x. So if I have log of x equals y, that means that 2 to the log x equals 2 to the y. So x equals 2 to the y. Sorry, 2 to the y. Okay, so let me write this again. X equals 2 to the y, so you don't get confused there. So this number inside here is a lot bigger than y. If I compare x and y, which one's bigger? X is a lot bigger.
Yeah. X is
Okay.
the one.
So something without a log on it is a lot bigger than something with a log in front of it. So when I take the log of something, I'm making it a lot smaller. So x before I took the log was some exponential thing. After I take the log, it's just y. So when you're thinking about that, just remember, if I want to compare x and log x, that log is a lot smaller. Okay, so let's use our method. Now, I didn't say anything about products. So if I have x squared plus 1 times 10x plus 5, then let's use our method and figure out the big O of this function. And we're actually also figuring out the big omega, but I'm doing it so that I'm proving a big O. So in this case, what's the largest term in the first sum? X squared. So I would replace that with x squared plus x squared. And that would be equal to 2x squared. Right? And my start value would be x greater equal to 1. Just for that one. Now I have to do a separate thing for the other sum. So for 10x plus 5, my largest term is x. So I would get 10x plus 5x, which will give me 15x. That's collecting my terms up. And x greater than or equal to 1 still works. So our start value is x greater than or equal to 1. And our constant, I multiply these out. I get 30x cubed, so my constant is equal to 30. So if this is f of x, then f of x is in big O of x cubed, where c equals 30, and my start value, x0, that's equal to 1. And when I write that, that means that f of x is less or equal to 30x cubed if x is greater than x0, which is equal to 1, greater than or equal to. So in the big O, I'm not trying to do anything with the product. I just do each of the sums separately, and then I multiply the results. And then I get my overall constants. Yes, Jenny?
The constant c doesn't mean anything. It could have
C
been...
is just the constant that goes in front of the function in the big O. So I just proved that f of x is less or equal to 30x cubed. That's what this proof was just now. Each of these makes something larger, so f is definitely smaller than this, right?
Could I have used, instead of 5x, I used just x, 10x plus x, so I have 11x.
But then x would need to be at least 5, right? If I want to replace 5 with x, then x has to be at least 5. Because I have to make it bigger all the time. Right? So if I were to do that, I can do that on another sheet. You're allowed to do it. You just have to start later. So that would be x squared plus x squared. 10x plus x, but in this case, x has to be at least 5 for x to be bigger. Right? So that's what I mean by finding my start value. If I want to replace something with something larger, I have to ensure that it's larger. So f of x is less than this, and that gives me 2x squared plus times 11x. That's equal to 22x cubed. So I have a different constant but a different start value. So it doesn't matter what you have as long as you just know the pair that goes together, a start value and a constant. So here again, I've just proved fx is in big O of x cubed, but here my constant is 22, my start value is 5.
Now, that works for the constant of 5. Can you replace the constant of 10 and get x squared plus x starting
Do you think I could ever get x squared as the big O of this function?
No, I mean,
X
like
cubed,
on the
you
right
mean?
side. Replacing
right
the 10
side?
with an x.
If I replace the 10 with an x, I
Can
could
you
start
do
with
that?
x. Yeah, that would be fine. I would get a smaller c, right?
Yeah.
So if I just put x there, then I would have to say x is at least 10.
Okay.
And then this 11 would go away and we'll just have a 2 as my constant.
But would it be x squared as long as x is greater than or equal to 10? Since, see, since we're replacing the 5 with the x, can we replace the 10 with the x and get x times x?
We can replace 10x with x.
But not with x squared.
We can replace it with x squared too, but we get a bigger big O function. I wouldn't be able to prove it's in x cubed. I'd be proving that it was in x to the 4th. Which it is, because x cubed is in, big O of x cubed is in big O of x to the 4th. It's a subset, right? So big O of 1 is a subset of big O of x is a subset of big O of x squared.
Yeah.
Am I doing it right?
Yeah.
Looks like it.
Everything in here is in there. That's right.
Yep.
Yeah.
So,
Big O of x cubed.
sorry, x cubed should be in there. Big O of x to the fourth. So my function's really in here, but I could prove that it's in there.
Right.
So
Which wouldn't help us at all.
I'd rather you prove that it's in here, but you can prove that it's in there. If I just say give a big O for this function, and I don't say give the smallest big O, you can do that. But this is the one I want.
But then we could just say it's an x of x, or big O of x to the x.
That's right. I could always put x to the x as long as I had regular functions in there. But what good would that do you?
None?
No comparison value at all. So the whole point is being able to compare things. David, your question.
I'm just, I noticed something, and I want to know if this is true. It looks like if you take those two functions and multiply them out, that it gives you a term with like a cubed in it.
That's right. It sure will.
Is that
What an
the same
amazing
thing?
coincidence.
Okay.
Yes, it works like that. That's why this works. So let's try it. If we multiply them out, we get 10x cubed plus 5x squared plus 10x plus 5. That's the largest term. So I could also do it that way. 10x cubed plus 5x cubed plus 10x cubed plus 5x cubed. Would be using my method again. And then I would have a different constant.
30x cubed.
That's 30x cubed. And then x should be at least 1.
And then what's the big omega of that?
Wow.
I know you've been
Big
talking
omega?
about a big O, but what's the big omega of that?
Well, anything that's smaller is the
Then
big
x,
omega.
Then x cubed.
Right.
Okay.
So it's actually, this is also big omega of x cubed. It's also big omega of x squared. Right?
Okay, because it's
Because I can prove
greater
that
than,
f
less
of
than.
x
Sure.
is greater than or equal to a constant times x cubed.
Okay.
Because it's bigger than 1 times x cubed, right? Because that's a sum. 10x cubed plus 5x squared plus a bunch of other stuff is bigger than x cubed.
Right. Okay.
So that's why f of x is in big theta of x cubed. Because I can prove that it's bigger than something times x cubed, and I can prove that it's less than something times x cubed. So that's the approximate growth. But it's not in big theta of x to the fourth, right? We could prove that it's in big O of x to the fourth, but it's not in big omega of x to the fourth. Because it's not bigger than x to the fourth, it's smaller than x to the fourth, so it can't be in big omega of x to the fourth. You need what?
I need to copy something you are covered in there. Take that paper out. There's another one. Yeah.
Oh, you need to copy this. That's fine. Okay, so these are very important in comparing functions. So what you'll be able to do is look at an algorithm, be able to figure out what the runtime is, and then you can compare two algorithms and see if they have approximately the same running time or which one is bigger than the other. So I might ask you to do some proof of which functions are bigger than others. So you're going to have to do induction proofs just like on the homework that's due coming up, that we had to prove that n factorial is less than n to the n. You might have to prove that n squared is less than 2 to the n. Or any one of those things in order. I put them in order, right? So if you were confused about logs, say you didn't know which one was bigger, x log x or x squared. Well, one thing I would do is I would make a guess, and then I'd try to prove it. So without doing a proof by induction, I could just take x log x is less than or equal to x squared, divide both sides by x, log x is less than or equal to x. If I'm not sure then I could raise both powers to the sides to the 2 to the log x, less than or equal to 2 to the x, but I know 2 to the log x is equal to x. That is surely less than 2 to the x. So if I don't know with a function, I can do some algebra until I do. So if you are not comfortable with logs, you can change it into exponents, which are a lot easier to see. The other thing you could do is say x squared is x times x. Those two are the same, and log x is less than x. So there's a couple of things that if you memorize them, they'll make it a little easier for you. Now if I have to prove this by induction, what do? What's the first step? Basis. So remember we start with 2 if we start with a log x. I actually don't have to start with 2 because I don't have the log x on the right side. So let's say x basis x equals 1. 1 times log of 1 equals 0. 1 squared equals 1. 0 is less than or equal to 1. That's true. Log of 1 is 0. This is the left-hand side. This is the right-hand side. No, it's not. 1 times log of 1. That's what that is. I assume that x log x is less than or equal to x squared. Just like my regular induction, I replace all my x's with x plus 1. Be careful about that right-hand side. With the square, you have to put x plus 1 inside the square. It's not x squared plus 1, it's x plus 1 quantity squared. Then I would start with the left-hand side. I'd multiply it out. That's equal to x log of x plus 1 plus log of x plus 1. Don't forget to put parentheses. I have to get this in terms of x log x, right? If I start out with something and I think it's hard, does anybody think this is hard? I go back and I start with the right-hand side and see if that's easier. Okay? You can start with the left or the right and get the other one. So if I start with the left and I go, not sure about that, try the other side. Okay, so let's try the other side, and if we don't do that, we'll go back and do that one. Okay? Whichever one looks easier is fine.
It looked easy if you just factored out the log x plus 1. Yeah, just factor out log x plus 1 on the right-hand side.
Then I would just get back what I started with.
Oh, okay, I thought that was what you were trying to prove.
No, that's not what I'm trying to prove. So let's start with the right-hand side of what I'm trying to prove, because I know I can write that in terms of x squared by multiplying out, right? X plus 1 squared is x squared plus 2x plus 1. So now I can replace the x squared with x log x. And I have to put, which way do I put? Greater than or equal to or less than or equal to? If I'm going to replace this with something smaller, then this is greater than or equal to, because that x squared is greater than or equal to x log x. Let's put x log x plus 2x plus 1. So I'm doing a substitution like normal. I just have to make sure I put the less than or equal to or greater than or equal to the right way. So I'm replacing x squared with something smaller. So now I want what? That x log x plus 2x plus 1 is greater than or equal to what?
X plus 1 log x plus 1.
X plus 1 of log x plus 1 times log of x plus 1. So let's try that. X log x plus 2x plus 1 greater to 2. I'll multiply this out. X log of x plus 1 plus log of x plus 1. since we're close to out of time, I don't want to finish this algebra for you because I think I'll mess it up in front of you since I haven't worked it out yet. So, but in general, you've got an idea of how you do an induction proof. This is the most important part, is figuring out how to write the left-hand side in terms of the left-hand side, or vice versa. You could do the right-hand side in terms of the assumes right-hand side, and then you have to do some algebra. We have sort of a magic step that looks at this and says what I'd like for it to be bigger than or less than, and then we have to prove that. You could prove that by induction too. So if you get to something and you don't know how to prove it with algebra, you can do it by induction. Usually you can reduce it again and again until you get something that you can prove. So let's do another example where I know the algebra is not so bad. Yeah, we're all for that, right? So n squared is less than or equal to 2 to the n for n greater or equal to 4. And someone needs to tell me why I picked n greater or equal to 4.
Because less than 4, it's not.
Because it doesn't work until we get to 4, right? So because 2 squared, actually n at least 2 might work. So 3 squared is 9. It's not less than 2 to the 3. So we have to start with n equals 4. 4 squared is less than or equal to 2 to the 4th. That's right. So we're happy with that one. So n equals 4 will be our basis. We have 4 squared equals 16. Is less than or equal to 2 to the 4th is 16. So that's true. We assume n squared is less than or equal to 2 to the n. We want to prove n plus 1 quantity squared is less than or equal to 2 to the n plus 1. Looking at this, I'd like to start with the right-hand side of the proof statement. Or I can start with the entire assume statement, which is something I like to do also. Doesn't matter. Let's start with 2 to the n plus 1. That's equal to 2 times 2 to the n, right? Which is greater than or equal to 2 times n squared. If I go from...
I always get lost when you do that. You got. I see where 2 to the n came from. 2 to the n plus 1.
Did you see where this came from?
No, that's where.
You need to work with powers. 2 to the n plus 1 is 2 to the n times 2 to the 1. Because I add powers. If you look at this and go to that, you should find it a little easier.
Okay.
Right? 2 to the n times 2 to the 1. Add the powers. 2 to the n plus 1.
Right.
Okay? Then if I multiply 2 to the n times 2 on both sides of the assume, I get 2 times 2 to the n is bigger than or equal to 2 times n squared. So I want 2 times n squared to be bigger than or equal to n plus 1 quantity squared. And then I would be done, because I would have 2 to the n plus 1 would be bigger than n plus 1 squared. So then let's multiply that out. It's greater or equal to n squared plus 2n plus 1. I can subtract n squared from both sides. I get n squared is greater or equal to 2n plus 1. You just want to keep doing this until you get down to a point where you believe the inequality that you have. Okay? If you don't yet believe this one, you could prove this by induction, which doesn't hurt. Okay, you could try some values and verify to yourself that this is true, or you could divide both sides by n if you wanted. N is greater or equal to 2 plus 1 over n. Everybody believe that?
Yep.
Yes.
Because 1 over n is less than 1, n is at least 4, so n is bigger than 2 plus 1 over n. So anything you can do to get to a point where you believe it is fine. If you can't get to that point, you would prove this by induction. So if you got here and you didn't know what to do, you just do a proof by induction. Basis, assume, proof. Because what you'll get is simpler than what you started with. If you notice, we had squares and powers, exponents. Down here we just have squares and linear terms. if you do induction one more time, it'll hopefully be even simpler. You could use a table, but that's not a proof. So that could verify it to yourself. So if you thought, oh, maybe Tiffany will believe this, and you look at a table and you verify it to yourself, that'll be okay. Okay, so this is true, so therefore these are true. So therefore, our final proof statement is true. 2 to the n plus 1 is greater or equal to n plus 1 quantity squared. And that's the end of the proof. So this little want step, that's kind of like using hypothetical syllogism. Right? So remember, if we had P implies Q and we wanted P implies R, we would say, we'd like to know that Q implies R, and then we'd figure out how to get it. That's what you have to do in these proofs. Yes?
So like a test or homework or whatever, that's proper notation, just put wants.
Sure. Because then I realize that after that, you're going to prove that statement, and then you're going to use it.
As long as you prove it backwards, right?
So I don't mind, doing little check marks going back up to verify that your proof actually really goes that way. Do y'all remember, like in geometry or something, your teacher would say, don't do things backwards? She'd say, figure out the answer by starting with what you want and then get, you know what I'm saying? No, you guys don't know what I'm talking about. This is a backwards proof. Take a look at this. This is a backwards proof. I don't know this, I don't know this, I do know this. Right? So this is not really a proof. A proof is a list of things that are true ending up with something that you want that's true. So I actually have to read this backwards for it really to be a proof. That's what I'm talking about. This is really the proof. This is true, so this is true, so this is true. This is what I wanted to be true, so therefore I can combine that with this.
Yeah, but you have that thing right above it too, where you
I
start.
know this is true. This is true.
Let's talk about the other thing up one.
This?
Yeah.
I don't know that's true. This is true. This I don't know.
The assume.
We assume this is true. This is always true. This we don't know if it's true. Well, this is true by assumption, right? Because this is from the induction step. Right, so part of it's always true, and part of it's true by the assume step. Okay, see y'all next time.